What's up, guys? Welcome back to the xHCI driver development series. So now we're at a point where we have solid infrastructure in place and we can properly communicate with the USB controller. So the next logical step would be to detect connected devices and implement port management functions. However, there is one crucial part that we must cover first before we can do that. In the beginning of the series, we've covered capability registers that report basic hardware and configuration information about the controller. However, there also exist extended capability registers. Here are the most common extended capabilities that can be present in your controller, and are more commonly found on consumer-grade hardware rather than emulated controllers. We might cover a few of these later on, but the one we care about right now is the supported protocol capability. You see, even though you can plug in different devices into the same physical USB slot on your machine, the actual connection goes to different controller registers depending on whether that device is a USB2 or a USB3 device. At this point, we only found out how many ports our controller has, but by reading the supported protocol capability, we will also know the ranges and port numbers of USB 2 ports and USB 3 ports. To find out where the extended capabilities live, we need to refer to the xHCI params register in the regular capability register set. The high 16 bits of that register encode the pointer to the extended capability space, and all you have to do is read that value, shift it left by 2 bits, or just multiply by 4, and add that offset to the xHCI base address, and that will give you the address of the first extended capability register. Now each entry is composed of the capability ID, the pointer to the next capability, and some capability-specific data, along with the payload. The next pointer field is again an encoded offset that you just have to shift left by 2. This means that in practice, the extended capabilities are arranged in a linked list and could look something like this. Now that we know the theory, let's jump into the code and implement it. Alright, so we'll start off in xHCI regs.h, and at the bottom of the file, let's define a 32-bit extended capability entry structure, which again consists of the ID, the next pointer, and the 2 bytes of capability-specific data. I'm also going to paste in a macro here that will just make the calculation of the next entry's address easier later on. Below that, let's also define an enum for the extended capability identifiers. Then, let's create the xHCI extended capability class that will make the traversal through the linked list a lot easier. The point of it will be so that you just have to hold the one instance of this class that points to the first extended capability, or the head node, and through the readNextExtCaps function, which we'll call in the constructor, it will automatically read in all of the next entries. In the constructor, we'll take in the address of the extended capability entry and just simply dereference it, assigning it to the M entry member. Great, let's now implement the readNextExtCaps function, and it has to first check if the next pointer is valid in the current entry, and if so, it will use the previously defined macro to get the address of the next entry. And that's it for the class. Simple enough. Let's now go back to our main xHCI driver class and declare the head node instance there. Let's also declare a new function to parse the extended capabilities. This will be a place to actually go through the extended capabilities list and detect the supported protocol capability. Great, so the first thing we'll do here is calculate the actual address of the first entry. And would you look at that, we already did it before, and stored it in a member variable even. How convenient. Alright, let's now instantiate the extended capabilities head. Let's also not forget to actually call this function, and we can do that right after parsing and logging the regular capability registers. Cool, so now that we have a working linked list of these extended capability entries, let's walk it, and for now just simply print out each capability's ID. And wonderful. As you can see, we've detected 2 entries that correspond to the supported protocol capability. Going back to the code, let's create a new file called xHCI extendedcap.h, where we can define specific structs for the extended capabilities. For now, we'll only have one struct in here for the supported protocol capability. Alright, so the first 32-bit D word is essentially the entry's header, which will be the ID, then the next pointer, and as part of the capability-specific data, it will have a minor and the major versions each being 1 byte. This will correspond to the actual USB protocol version. The second D word is just a name field which contains the letters USB in space. The third D word is very important as it will contain the compatible port offset, or the number of the port where this range begins, and the number of ports that this protocol includes. So basically, each supported protocol capability describes a range of ports for a given protocol version, whether it's USB2 or USB3. And finally, the fourth D word is just a slot type, which we won't need to use. Finally, I'll just define a helper constructor here that, given a pointer to the entry, it will just read in each of the D words 32 bits at a time. Great. Now let's go back to xHCI.cpp, where we parse the extended capabilities, and replace our old print statement with some slightly more useful code. First of all, let's check if the entry is the supported protocol capability. And if so, let's just initialize our supported protocol struct as a local variable here. Then, and this is important, let's read the first port in the range and make it 0-based, since the capability considers that port indices start with 1. Then the last port in the range is simply the first port plus the port count, and again, -1 to make it 0-based. Then we can check if the major revision version is 3, meaning that this is a USB 3 protocol port range. And if so, we'll need to keep track of this range somehow. I know there is most likely a much better way, and maybe even an easier way to do this, but I will just create a C++ vector as part of the xHCI driver class, and simply just add every 0-based port number for the USB 3 protocol into it. Then, to check if the port is a USB 3 port or not, we can simply just search for it in the vector, and if it's found, then it is a USB 3 port. Otherwise, it's USB 2. Again, this is not the most performance-oriented approach to tracking USB 3 ports, but the number of ports that the controller supports is not that big, and this function will not be called on any hot paths, so for now this should be fine. Alright, let's now go back up to our start device function and test out our protocol detection mechanism by iterating over every port in the controller and printing out which protocol it supports. Let's now compile and run this and see what we get. Alright, amazing. As you can see, ports 0 through 3 are USB 3 ports, and ports 4 through 7 are USB 2. This may not mean a lot to you right now, but this information will become very important in the next tutorial when we start dealing with port management registers and resetting the ports, since the reset logic is quite different for USB 2 versus USB 3 ports. Additionally, it's just going to make dealing with other extended capabilities much easier later on, now that we have this infrastructure in place. Well, that's it for today. Please comment down below if you have any questions, comments, or feedback, and I'll see you in the next one.